Okay, when we think about acids, acids have H plus, the acid, or hydronium, H plus. And so the more positive the hydrogen is, the more acid or acidic it is going to be. And so when we look at that, though, you know, the electronegativity, when we look at the electronegativity of oxygen, it's 3 point something. Depends on what book, 3.5 or 3.6, 3.4, what book you're using, but around there. And it doesn't seem to change, but electronegativity, En changes depending on the bonding environment. Depending on the bonding environment. And so those numbers that we see in the table, like fluorine's a 4.0, well, it's not always a 4.0. It depends on what it's bonded to and the bonding environment around there. And so when we look at these, you might think all these are the same, you know, acidity-wise, because they all have an HO bond. They are all going to have the same delta En, right? But they aren't all the same, you know. Oops, actually, forgot to color. Oh yeah, sorry. Okay, so talking about the acidity, the positive charge that's going to be built up on these is going to be different. And so, for example, on HOBr, you know, it's going to have a smaller positive charge build up than on HBrO4. So why is that? This is going to have a bigger positive charge buildup than that. Can somebody explain that to me? There are two ways of explaining this. Unless, does somebody have the answer?
HBr4, Br17.
Yeah. Okay. So that's one way of explaining it. One is you look at the formal charge. If you look at the formal charge here, the formal charge is 0. I forgot the R. There. You look at the formal charge there, it's 0, but when you look at the formal charge here, it's plus 3. And so what's happening here is that, well, plus 3 means it wants more electron cloud or it wants less electron cloud. It wants more. Electron cloud's negative, so it's going to pull the electron cloud closer to it. And so what happens is that normally oxygen versus bromine, oxygen wins the tug of war, but this bromine's not normal. This bromine is starved for electron density. And so what happens is this, it pulls it this. And so we end up with something like this where the oxygens pull off the electron cloud. And so because of this bromine, well, first off, the oxygens are sucking the electron cloud off this bromine, making this bromine very electron poor, and then that in turn is going to suck electron density away from this, or at least put a bigger fight with this oxygen, such that the hydrogen becomes less. Whereas here, look at all these lone pairs that belong to it, and so oxygen is more electronegative in this case. And so it depends on how the cloud is being distributed in that. This is called the inductive effect. The other thing is oxidation state. You know, when we look at the oxidation state here, the oxidation state on bromine is -1. Or no, oxygen wins is +1. The oxidation state on bromine here is +7. And so there's going to be a huge difference in oxidation states as well. +1 here, +7 here. So this bromine is quite a bit different in terms of both formal charge and oxidation state. Do you see that? And so in other words, bromine's behavior changes, the more thirstier it gets for electron cloud density. And so this is the ranking. The strongest of these acids will be this one, HBr4, followed by these. Does that make sense? In other words, it's how the electron cloud is going to be distributed. And so the more the electron cloud gets sucked away from hydrogen, the more acidic it becomes. And the way the electron cloud gets sucked away depends on the rest of the structure, how the electron cloud's distributed in the rest of the structure. It's going to show us. So I've spent a lot of time on this, a lot more than usual. That's because this structural stuff is very important. Properties. And this is the video I was trying to show the other day. We'll watch it now. This talks about shapes and health. Kind of a long video. But it's a pretty interesting video. It's old though. But still relevant today because you'll see.
This is a production of the Chemical Education Material Study. More than 1 billion species currently exist. We now know that a principal factor in this large number is the billions of ways that 4 rather simple chemicals can vary their sequence in forming DNA genes. We are also discovering that many illnesses can be identified at the molecular level. This provides information for the design and synthesis of molecules, which can be used to treat the disease. If we examine living cells under the microscope, like these plant cells, or these bacteria, or this animal tissue, we can see the movement, growth, and cell reproduction, which are the result of successions of chemical reactions. In attempting to control these reactions, physicians have used various substances, some from nature, and some synthesized in the laboratory. Many of the compounds found to be useful were discovered by trial and error. One such compound was sulfanilamide. Let's demonstrate the effect of sulfanilamide on bacterial growth. A nutrient medium in a petri dish is used to sustain growth of bacterial organisms. These bacteria, harmful to humans, are carefully transferred from a stock preparation. They are gathered in a wire loop and streaked onto the nutrient medium in both compartments of this dish. A small piece of sterilized filter paper is wet with a sulfanilamide solution and placed on the bacteria in one compartment of the petri dish. The dish is placed in an incubator for 24 hours. During that period, seen here in time-lapse photography, the bacteria multiply and become visible as large colonies everywhere except in the area around the paper disc. The clear zone shows that bacterial growth has been stopped. This inhibition is due to the sulfanilamide from the disc. How does sulfanilamide stop the growth of these harmful bacteria? First, let's examine the function of one of the key molecules that exists in the bacterial cells. It is called para-aminobenzoic acid. Using a geometric symbol retaining the general contours of the molecule, we'll follow its action within the cell. In the cell with the acid is an essential bacterial enzyme. In order for the enzyme to perform its active role, it must first combine with the para-aminobenzoic acid. Only then can the enzyme catalyze the further reactions necessary to cell life. When we examine the structure of the acid molecule and compare it to a molecule of the drug sulfanilamide, we find that they are much alike. This large portion of each is identical. The electron charge distribution in each molecule is also similar, and their general configurations are the same. Using geometrical representations again, let's include sulfanilamide in the bacterial cell along with the normally present acid molecule. The sulfanilamide too can react with the enzyme. But the sulfanilamide not only fails to activate the enzyme as a catalyst, it also prevents the acid from doing so. Thus, metabolism stops, and the bacterial cell dies. The effect of sulfanilamide on cell growth was found by trial and error. But the discovery that sulfanilamide is structurally similar to an essential molecule accounted for the action of the drug. This principle of structural similarity helps us to predict which drugs might be effective against specific diseases. Consider, for example, the use of drugs in the treatment of cancer. By means of tissue culture technique, human cells are kept alive for microscopic observation. Here are normal human skin cells under the microscope. In time-lapse photography, cellular activity appears accelerated. We know of very few differences between the chemistry of normal cells and these cancer cells. One remarkable difference, however, is that the cancer cells grow faster. And another difference is that during the faster growth, the cancer cells use abnormally large amounts of a substance known as uracil. Can a structural modification of the uracil molecule be used to disrupt the fast growth of the cancer tissue?
Let me just pause it for a second. This is a color coding here. Do you know what black represents? Carbon. White, red, and blue. Nitrogen. Blue represents nitrogen.
Let's follow some of the steps a biochemist takes in answering such a question. He is familiar with the visible parts of a single cell, like this one undergoing division. We see a set of dark ribbons in the middle of the cell. These dark objects are chromosomes, and they are intimately connected with the process of cell growth. The biochemist has learned to collect chromosomal material from cells and has found that it is composed of deoxyribonucleic acid, or DNA. Because DNA is a large, complex molecule, it is helpful to break it into its component parts and identify them. These component parts can be separated from each other by the technique of paper chromatography. After treatment with an acid, a small drop of the chromosomal material is placed on this large piece of filter paper. paper is rolled into a convenient shape for the next procedure. We have selected a solution in which the chromosomal material is readily soluble. This is placed at the bottom of a glass cylinder. The solvent is drawn up the filter paper by capillary action. After 12 hours, the solvent front has risen this far. The filter paper is removed and allowed to dry. It is then rolled in the opposite direction and put back in a different solvent. This will ensure a further and better separation of the molecular components. These components are not visible under ordinary light, but if we place an ultraviolet light under the dried paper, we can see that the solvent has distributed the components of the chromosomal material. This distribution has occurred because the solvent front competes with adhesion to the paper for the chromosomal materials, so the components move according to their molecular size and solubility. Thus, different compounds derived from the chromosomes are separated. We'll cut out one of these marked areas and dissolve the material from the paper with another solvent. Now we can analyze the dissolved material with an infrared spectrometer. A characteristic spectrum is produced by each component separated in the chromatography procedure. The absorption spectrum produced by one of these extracts is compared with the known absorption spectrum of the chemical thymine. Apparently, chromosomes contain thymine. Similar analysis of the other components shows that each has its own characteristic spectrum. Identification shows that besides thymine, chromosomes contain adenine, guanine, and cytosine. How do our uracil molecules, which are present in such large amounts in cancer cells, relate to the constituents we have extracted from the chromosomes? We know that these constituents, along with other building blocks, are necessary to make DNA molecules, which in turn have a part in forming the chromosomes. Biochemists have shown that uracil is the substance from which thymine is formed. Without uracil, thymine will not form, preventing the synthesis of DNA, which in turn prevents the formation of the chromosome. When we examine the molecular structures of uracil and thymine, we find that there is but one position in which these structures differ. To convert uracil into thymine, a hydrogen atom here must be replaced by a methyl group, such as this. Let's symbolize uracil with its hydrogen atom, like this, to follow its action within a cell. First, a chemical group called a sugar phosphate residue becomes attached to the uracil molecule. The modified uracil compound then forms a complex with an enzyme. Somehow the enzyme converts the hydrogen into a methyl group to form the thymine compound. This molecule is then freed for eventual synthesis into the DNA chain. How can we disrupt this mechanism and stop cell growth? Clearly, one point of attack is the original uracil molecule. This molecule can be altered in many ways. One of the most promising has been to replace this hydrogen with a fluorine to give 5-fluorouracil. 5-fluorouracil has a number of advantages. First, the hydrogen and fluorine are almost the same size, so that both molecules should fit into the enzyme. Second, the chemistry chemistry of a carbon-fluorine bond differs from that of a carbon-hydrogen bond, so that the enzyme might find it difficult to replace the fluorine with a methyl group. And finally, the changed polarity may allow the fluorine compound to adhere more firmly to the enzyme than would a uracil compound. Thus, we predict that the 5-fluorouracil, just like the uracil, will attach itself to a sugar phosphate residue and then fit into the same place on the enzyme the uracil would have used. But once in place, the strong bond to fluorine will prevent the enzyme from replacing the fluorine with a methyl group. And finally, we predict that the strong polarity of the 5-fluorouracil will cause such strong adherence to the enzyme that the normal uracil compound will be prevented from reacting, and that, with the enzyme blocked, the essential chromosomal material cannot be made, and the cell will die. Let's test this prediction in the laboratory. Here are two cultures of cancer cells. Those on the left have been treated with 5-fluorouracil. Compare the action of these cells to that of the untreated cells on the right. The untreated cells continue to show rapid growth. The 5-fluorouracil treatment is seen to stop cell division, produce cellular enlargement, and eventually contraction and death. But are we sure that the cancer growth is stopped in the manner we predicted? Instead of the 5-fluorouracil blocking the enzyme as we have suggested, and using this means to kill the cell, is it possible that the 5-fluorouracil is incorporated into the DNA, inhibiting its function? To determine where the 5-fluorouracil is acting, in the enzyme or the DNA, let's conduct an experiment on some human cancer cells grown in the laboratory. A sterile pipette is used to transfer the cells into a large flask, which contains a nutrient medium. This permits continued growth so that we will have enough cells for our experiment. The cells are kept in suspension by a magnetic stirrer and incubated for several days. Here is specially prepared 5-fluorouracil containing radioactive carbon-14. By tagging the 5-fluorouracil with these radioactive atoms, we can determine where the 5-fluorouracil goes in a human cell. We'll add a small amount of the radioactive 5-fluorouracil to the living culture. In about half an hour, these radioactive molecules will be incorporated into the cancer cells. Cancer cell suspension is poured into large cups to be spun in a centrifuge. The spinning collects the suspended cancer cells into a pellet on the bottom of the cup. The liquid is discarded. By this means, the cells from large volumes of the culture medium are finally concentrated into one cup. The cells are then resuspended in cold sodium chloride solution to dissolve the DNA. The low temperature retards enzyme action. this cell suspension is placed in a blender. The violent action of the blender fragments the cells to facilitate dissolving DNA. After storage overnight in a refrigerator, the DNA dissolves, and then the solution will be spun very rapidly in a centrifuge. This spinning action separates the residual cell proteins which contain the enzymes. A high-speed centrifuge is required because the large size of the DNA has made the solution viscous. After the centrifuging, the liquid fraction contains the soluble DNA. The pellet contains the undissolved residue. According to our theory, if the 5-fluorouracil is incorporated into the DNA molecule, radioactivity should be detected in the liquid. Otherwise, it should be found in the pellet. The next step is to concentrate the DNA. The liquid is drawn off and injected into alcohol, which precipitates the DNA. These threads of DNA material can be readily collected on a glass stirring rod. A sample of the DNA fraction is removed for measurement of its radioactive content. The protein pellet is retrieved from the centrifuge tube. The meter shows that there is no radioactivity in the chromosomal material. However, the protein fraction does show radioactivity. The experiment proves that the radioactive 5-fluorouracil is not incorporated into the DNA. Though the chemistry is oversimplified as portrayed here, it does show that the structural similarity of 5-fluorouracil to uracil is of crucial importance in its ultimate effect, the enzymatic synthesis of genetic material. 5-fluorouracil is currently one of the most effective chemotherapeutic agents for treating certain types of skin cancer and colon cancer. About 40 anti-cancer agents are in clinical use today. For example, chemotherapy with methotrexate can lead to complete remission for 97% of children treated for acute lymphocytic leukemia. But we need even more effective and less toxic chemicals, especially for lung cancers and brain tumors. In the past, most medicines have been discovered by trial and error, even by accident. Aspirin, the most widely used medicine in the world, was used for almost 100 years with no idea as to how it reacted in the body. Modern techniques are allowing us to learn about living systems at the molecular level and what changes cause loss of health. Now some mechanisms are understood. We are beginning to be able to design molecules the living system needs for recovery.
Yeah, this is a series produced in Berkeley. radioactive material?
Yeah, that he said at the end that it doesn't, like, it doesn't go inside of your body, so where does the other stuff go?
The radioactive materials, they had the cells there, and so the radioactive material is being incorporated into the cells. And so the radioactive material, they just make it by, if you take the 5-fluorouracil, if you take that and then take one of these carbon atoms here, and this carbon atom is either going to be carbon 12 or carbon 13. What you can do is you can synthesize this so that this carbon atom ends up being carbon 14, the rest of the structure. So you have that molecule, the chemotherapy, that's a chemical therapy agent. You have that molecule with a radioactive carbon atom incorporated into it. And so what that allows you to do is it allows you to follow it with a Geiger counter. Wherever that molecule goes, you can follow it with a Geiger counter. And so this molecule, the 5-fluorouracil, the question was it going into the DNA and then screwing up the DNA, or was it going into the enzyme and preventing thymine from being produced? And so what they did was they separated the DNA from the enzyme, and then at the end, the pellet was the enzyme, the DNA was the chromosomal material that they talked about, and then they saw that the DNA had no radioactivity, whereas the enzyme did. And so the question was, I mean, somebody could argue that, hey, it gets incorporated in the DNA and screws it up. Well, they can't argue that anymore because it doesn't get incorporated into it. And so that was the last part of that. But the radioactive, in biochemistry, this is very common. Biochemists, they want to track where, if they have some kind of drug, they want to find out where in the body it ends up. And so what they'll do is they'll tag atoms with radioactive isotopes, and they'll be able to follow it. Okay. So this is called radioactive tracing. They don't, not just biochemists, but my friend he got a job at the oil refineries. His job was to inject tritium into the pipes. They inject tritium into the pipes, and then he follows the pipes with a Geiger counter. And wherever he detects radioactivity, there's a leak. And so he's just looking for leaks using radioactive tracer, which is radioactive hydrogen. That was his job. Okay, let's go here. Since structure is important, structure, polarity, this kind of stuff is important, we need to spend this extra time talking about this chapter here. Do you recognize this? This is called propane. It has 3 carbons. Hydrogens there. Did we take a break yet? Yeah, we did. That's right. So, all right, draw a wedge dash representation of the molecule shown below, and then criticize the statement, carbon atoms in the molecule lie in a straight line. Well, we would draw the wedge dash diagram for this. After you get a lot of practice. You know how organic chemists would represent propane? In organic chemistry, you just see this. Okay, you saw that's propane. What you're doing is you're just drawing the carbon-carbon bonds with lines, and if there's some other element in there, then you change it. Well, we got this exact. So propane would look like this. If you do enough of these. Now, we could twist it, these are called conformations, so we could twist it to the hydrogen. If we twist this, then the hydrogen forms another zag. See, zag. So so they did it, they twisted it. So I drew my first carbon different. You know, I had one hydrogen pointed straight up. So what they did is they just rotated this group, the CH3 group. It's called nothing group. So they can just rotate this so that the hydrogen is now on the plane here. So we get this. We can rotate this one so the hydrogen goes on the plane. So it looks a little different than what they have. But it's okay. Those are called conformations. Yeah, the bond angles are, it's tetrahedral, so the atoms cannot lie in a straight line. That's what they say there. Benzene is a planar molecule in which the carbon atoms are arranged in a hexagon. The Lewis diagram of this molecule has a geometry that accounts for the observed shape of the molecule including the bond angles. Draw this diagram. Experimental evidence shows that this diagram does not describe the structure of benzene accurately. Do benzene. Benzene is an important molecule. And so it's propane. If we do benzene, it's a 6 carbon ring. Like this. All these carbons are trigonal. All these carbons are trigonal planar. Do you see that? We have this alternating double bond. Well, it turns out there's a resonance form for this. The resonance form for this is going to look like this. Basically, what we're going to do is we're going to swap. You see? So if I just swap the electron, we'll generate that. And then if I do it again, we'll revert back to this. There are two resonance functions of this. But you know, this is what we said. Remember localized versus delocalized? Somebody remind me what localized versus delocalized. It would be the bathtub analogy. The bathtub analogy would be like 2 feet, 1 foot, 2 feet, 1 foot, 2 feet, 1 foot. But if the water can spread about like it can here, then am I going to get 2 feet, 1 feet, 2 feet, 1 feet? No, what would I end up with? In other words, the electrons can be delocalized over the entire ring. So what is it going to look like? What it's going to look like is it's not going to be 2 feet, 1 foot, 2 foot, 1 foot. It's going to be 1.5 feet rather than that. So what I end up with is a hybrid structure. The hybrid structure is going to be the average of those two. In which all the bonds are the same. And then the double bonds are just spread out over the entire ring. So this would be the hybrid structure. For organic chemists, the shorthand way of drawing benzene is like this. It's benzene, where you delocalize the double bonding electrons over the entire structure. See what the book does. The book does this, but they say it's not accurate. Yes, that's not accurate. It is a resonance form. And we got this resonance form here, but the true structure is going to be a hybrid because when we have resonance, that means we have potential for delocalizing electrons. And so if we look at the benzene, See, this is one of the Lewis structures. This is one of the Lewis structures, but essentially it's delocalized over the entire ring. Show that. This is one of the Lewis structures. This is showing the delocalized. You see the dotted bonds here? One of them delocalized. When you get into organic chemistry, then you see these are some models here. This benzene ring. This is the Wikipedia page. These are the resonance structures. This is what's happening when we look at the orbitals. This is more advanced. This is what you do in Chem 1A. Look at these orbitals, the localized bonds, delocalized bonds. Something called the delocalized bonds. Benzene.
So, oh, that's Chem 1A.
This is a Chem 1A. This is not Chem 4, so we're not going to talk about this at all. Chem 1A. And so they leave it hanging here, as they say, shows the diagram does not describe the structure of benzene accurately. Well, if it doesn't describe it accurately, then why bother? Well, there's a reason. 73, describe the shapes of C2H6 and C2H4. In doing so, explain why one molecule is planar and the other molecule cannot be planar. That's when you see the structures, then you'll know why one's planar and the other is not. I mean, one is ethane. What are the geometries around each carbon? What are the geometries around each carbon? Molecular geometries. Tetrahedral and tetrahedral. Whereas in the other, C2H4 looks like this. In C2H4, what's the geometry around this carbon? Trigonal planar and trigonal planar. This molecule is flat, like a pancake. It's just planar. This cannot be flat. Right? So one's called ethene. Take a look at ethene and the structure of that. Yeah, all hydrocarbons are non-polar. It doesn't matter, the shape or whatever. They're just all non-polar. And so maybe we can get a 3D. This would be like a 3D one here. No, we don't have it. Ethane cannot be flat. We can see it here, the ethane, the tetrahedral is ethene, with the double bonds, it's just plain flat. NaCHO2 sodium, this is called formate. Sodium formate is the way an inorganic chemist is most likely to write the formula of sodium formate. They tell us. Write the formula of the formate ion as an inorganic chemist is likely to write it. I don't know. Oh, this is the formate ion here. Formate is what happens, like acetate, you know, like formate forms formic acid, and if we lose the H plus, then we're left with formate. So formate originates from formic acid. Acetate originates from acetic acid. So acetic acid would look something like this, except rather than having a hydrogen, you have a methyl group here, and that would be acetic acid. Draw two different Lewis diagrams of C4H6. Well, we could have straight chain and we could have branch chain. We could also have different positions for double bonds. C4H6, yeah, it's different positions for double bonds and triple bonds and that kind of stuff. So these are, what do we call these? Isomers. No, these are all isomers, C4H6 and they have. But it's,
They all have different properties.
yeah, they'll have different properties, right? Because they have different structures. They end up having different properties. And so in organic chemistry, you try to draw all the possibilities. So you practice different isomers. And the number of isomers go way out the more carbons you have. C4H10O is the formula for diethyl ether. The same group of atoms is attached on either side of the oxygen. So diethyl ether was one of the first anesthetics used, but it's largely been replaced by safer anesthetics. Diethyl ether is very flammable. Well, you know, when we have one carbon, this is called a substituent. One carbon substituent is called methyl, CH3. A two carbon substituent, like this, which would be C2H5 or CH3, CH2, called ethyl. And so we have two of these ethyls attached. So this would be diethyl ether. Compare Lewis diagrams for CCl4 carbon tetrachloride, sulfate, perchlorate, and phosphate. Identify two things that are alike about these diagrams and the way they are drawn. From these generalizations, can you predict the Lewis diagram for SeO4 2-, which would be called selenate, CiO4? Yeah, you'd be able to predict. And so what they're doing is everything has an octet. They aren't minimizing the formal charges here. They're just leaving everything as an octet. They're all tetrahedral. You see that? And so it'd be pretty easy to do the other drawing. They all have the tetrahedral shape. What are the shapes of the following? 1,2-dibromoethene. Now the 1,2, the numbering system comes from where the bromos go. It's dibromo, those two bromines. Do you put them all on one carbon, or one on one carbon, one on the other? And so we number the carbons. Oh, here, it says the bromine atoms are different carbon atoms. I guess we don't draw. Acetylene. Acetylene has a carbon-carbon triple bond. It's linear. N-butane. We drew that one before. And that pretty much finishes up the homework there for chapter 13. We're going to start a new chapter, chapter 14, which is gases part 2. Yeah, gases part 2. Yeah, gases part 2. We're going to look at something called the ideal gas law and gas stoichiometry and gas mixtures. Okay. And so, chapter 14, gases part 2. Learning objectives. We have something called Avogadro's law, which I've talked about a little bit before. Avogadro's law, all that says is volume is proportional to the number of particles. So if you have twice as many particles, you'll have twice the volume. 3 times as many particles, 3 times the volume. But we don't count particles, we count moles of particles because there's just too many particles. So if you double the moles, you'll double the volume. Triple the moles, you'll triple the volume. So the volume is directly proportional to the number of moles, i.e. the number of particles. So this is Avogadro's law here. Avogadro's law just says, this. Let's say we're looking at this reaction, it's oxygen. 1 mole of oxygen plus 2 moles of hydrogen yields 1 mole of H2O. No, sorry, 2 moles of H2O. And we're going to do H2O as a gas, not the liquid. Okay, H2O gas. And so all this says is whatever size box of oxygen, this is my oxygen here, I'm going to need twice as much hydrogen, so it'll be double the size of the box here. And so in this case, we'll put some numbers higher. If I have 50 milliliters of oxygen, I'll need 100 milliliters of hydrogen because I need twice as much hydrogen as I do oxygen. In this case, I'm going to form 100 milliliters of H2O gas. And so the volumes are like this, 50, 100, 100. In fact, this is called the mole ratio. It's a 1 to 2 to 2 mole ratio. But this could also be called the volume ratio. If I had 1 liter of oxygen, how many liters of hydrogen would that require? 2. And that would form how many liters of water? 2. But there's one restriction on that, and the one restriction is that they all have to be gases. If I change water to a liquid, then it doesn't work. You know, this works because this is a gas, but the H2O liquid occupies a much smaller volume than H2O gas, and so it's got to be all gases that we're comparing. Okay, I'm going to stop here. We're done.